Okay, let's do this question. So it says, find V1 and V0 in the circuit using nodal analysis. So they give us this circuit diagram and they want us to find the voltage V1, which they labeled right here, which is the voltage at this node. And they want us to find the voltage VO, which is the voltage across this 1K resistor. Now we're going to use nodal analysis to solve this. So let's begin to write the node method at each node. Now, before we do that, we know this is going to be node 1. We know this is node 2. And we have one more essential node at the bottom here. So we're just going to take this node as the reference node. So we know this is going to be our reference, right? Now let's begin to write our equations. So we can say node voltage at node 1. We know we're going to assume the current is leaving each node. So we have this 12 milliamp source that's going to be entering the node. So instead of it being positive, we're going to treat it as a negative current. So we're going to say negative 12 times 10 to the negative 3. Plus, we have a current that's going to be leaving this node. That's what we're assuming. So the current's going to go this way. Therefore, we're going to write it in terms of Ohm's law using the voltage and resistor relationship. So that's going to be V1 over 3K plus we have currents leaving going up to this branch. We know this is going to have a current source of 2 milliamps. So we have plus 2 times 10 to the negative 3. And finally, we have current going this way in this resistor here. So we're going to take the difference between the voltages at these two nodes and divide it by the resistance, which is 6,000. We have plus V1 minus V2 over 6,000 equals 0. And we want to get rid of the denominators, so we're going to multiply each term by 6,000, right? So when we multiply each term by 6,000, we're going to get negative 72 plus 2V1 plus 12 plus V1 minus V2. All of that equals 0. And when we start to simplify this, we're going to get 3V1 minus V2 equals 60. So this is going to be our node voltage equation for node 1. Now let's do the node voltage at node 2, which is going to be right here. So let's write that down, node voltage at node 2. Now we have the current source coming in, so we're going to treat it as negative. We have negative 2 times 10 to the negative 3, right? Plus, we're going to assume the current is flowing in this direction, so we're going to have the voltage difference, V2 minus V1 divided by 6,000. Plus, we have the current in this branch here. We're going to have V2 divided by 6,000 because we want to write it in terms of Ohm's law. Plus, we have a current that's going to be flowing in this direction here, right? So what's that going to be? Now, when we look at this, right, we know we can add these two resistors because they're going to be in series, which means the same current is going to flow through them. So once we add these two resistors, we know this resistor and the equivalent resistance is going to be parallel, which means the same voltage that is in this 6K resistor is going to be in the equivalent resistance here of 3K. So when we find the current in this particular branch, we're going to have V2 divided by 3,000. We're going to have V2 divided by 3,000, and all of that equals 0. Now we're going to simplify this to get rid of these denominators. We know that LCD is going to be 6,000, right? So we're going to multiply each of the terms by 6,000. When we do that, we're going to get negative 12 plus V2 minus V1 plus V2. Now we know 3,000 can go into 6,000 two times. So we're going to have plus 2V2 equals 0. Now when we start to simplify this, we're going to get negative V1 plus 4V2 equals 12. Now this is going to be our second equation. And this is going to be the node voltage equation at node 2. Now when we look at this, we have two equations and two unknowns. And those two unknowns are the same unknowns in both equations. Therefore, we can either use simultaneous equations or we can use the matrix method. I'm just going to use the matrix method. So when I set this up, I'm going to have a 2 by 2 matrix. We know the unknowns are going to be V1 and V2. Now let's start to fill out this matrix. I know for the first row, I'm going to have the first equation. So that's going to be 3. And we have -1. And that equation is going to equal 60. Now for the second row, we're going to have -1. We're going to have +4, and that's going to equal 12. So we're going to take the inverse of matrix A and multiply it by B. So when you take the inverse of matrix A and you multiply it by matrix B, you're going to get V1 equals 22.91 volts and V2 equals 8.73 volts. Now let's scroll back up. The question wanted us to find V1, which is the voltage at this node, and V0 in the circuit. Now we found V1. Now they want us to find the voltage V0, which is the voltage across this 1K resistor. So we found the voltage V1. So we know this is one part of our answer. Now to find the voltage VO across this particular resistor, now there are a few ways we can go about this. We can either do a KVL at this loop, right? We can find the current going through this branch. Once we find the current going through this branch, we can then multiply that current by this 1K resistor to give us the voltage VO, or we can just use voltage division. So what I'm going to do is I'm actually just going to use KVL. So I'm going to use KVL at this loop here. I'm going to label this loop 1, right? So when I do KVL at this loop, I'm going to assume that this is a voltage drop from plus to minus, from positive to negative. This is a voltage drop from positive to negative. And we know this is a voltage drop here, right? So we're going to assume this is also going to be positive to negative because of this voltage. So I'm going to start walking around right here at this particular resistor, right? So when I walk around this resistor, I know I'm going to be looking for the voltage. Now we know the voltage is going to be the same voltage at node 2, which is V2 here. So we know that's going to be negative. We just found V2, 8.73. So let's write this as KVL at loop. So we're going to have negative 8.73 when we walk around this resistor. Now when we come up here, we're going to be entering the positive terminal. So that's going to be plus the voltage across this resistor. We don't know, but we do know that there's going to be a current flowing through that resistor. So we can just label the current here. We can call it IO. So we know we're going to have a current going this way, and that's going to be the current IO that we labeled. So we're going to say IO times this 2K resistor is going to give us the voltage across this resistor here. So when we write that down, we can say plus 2000, which is the value of that resistor, and the current is IO, plus, because we know we're entering the positive terminal as we continue to walk around, and we know this current is going to be the same current that's going to flow in this resistor. So instead of writing the voltage VO, we're actually going to write it in terms of Ohm's law, and we're going to say IO times 1000. So we're going to say 1000 times IO, and we know all of this should equal 0 because Kircchoffs voltage law says the sum of voltages in a closed loop must equal 0. So when we solve for this now, we're going to get 3000 IO equals 8.73. Therefore, IO equals 8.73 divided by 3000. When you put that in your calculator, that's going to give you IO equals 2.91 milliamps. So we know the current IO is going to be 2.91 milliamps, right? So we know this current IO is 2.91 milliamps. Now to find the voltage, VO, which is the voltage across this 1K resistor, because we know the current flowing through this resistor and we know the value of this resistor, we can therefore just use Ohm's law. So we can say VO equals IO multiplied by the resistance. We know VO equals IO is going to be 2.91 milliamps. So we have 2.91 times 10 to the negative 3 multiplied by the resistance, which is going to be 1K. So we can write 1000. So when you solve for this, VO equals 2.91 volts. So this is going to be our answer for the voltage across that 1K resistor. We're going to get 2.91 volts. Now that we have found the voltage VO, we have successfully solved this problem. So as you can see, we still need to know those techniques such as Ohm's law, KVL, voltage division. They're all going to come back to us. So we have to be very efficient and fluid in those techniques that we have already mastered. Because once we find the voltages at each node, sometimes we're going to have to pull out some of those other tools we already learned to finish solve for different parts of this circuit. So this was an excellent problem. If you have any questions, leave them down below.